DraftScience video on the subject of inertia. Yes, I did begin the paper on that subject. This one seems like kind of the slam dunker. This one's just so... the school of fish thing is in here, so maybe I'll throw a couple of images of fish in here. But it's just such a good metaphor, so I do like it. Anyway, so link below to what's written so far, and I guess I'll add a conclusion of some kind and maybe some more bits, but I don't really want to have to explain the entire mechanism. Just most of it. Don't want to be dependent on the entire theory of a kinetic energy field distribution thing. But anyway, so what am I going to talk about if I didn't talk about that? Yeah, so anyway, that's where it sort of leads ultimately, and I just don't want to... I want to keep those in separate papers, but we'll see what happens. See if... I think this is enough. We'll just see if it's enough. But anyway, so what did I want to get to? All right, so the idea is the idea of inertia, velocity, right? And what I do is I compare it. I say, well, basically, this sentence is pretty good. An average physicist might say inertia is velocity, and velocity begins with acceleration. While I agree this is true, it's not the complete truth. Inertia really begins with E equals mc squared. So, the basic argument is that matter is quanta, little bits, moving the speed of light. So it's like they're photons, basically, of a kind. Either going to be recognizable as photons or not, depending on whether they're released at a frequency. But regardless, and that all the nuclear bits, all the quarks, the proton, neutron, electron, are all collections of these things, and that they're all in conservative circular orbits, in the sense the conservation is that it goes down, it goes back up, it goes left, it goes right. And I would argue that they are kind of a flat geometry, that they spin in one dimension, well, two dimensions, and that's it, and that they can move in only one dimension, essentially, at a time, so to speak. The movement in the dimensions is all separate movement. It's not in any way, there's no diagonals, so to speak. And that accounts for any real velocity versus apparent velocity. Your real velocity is how much you moved in real dimensions. And those dimensions, they're kind of arbitrary. I mean, you can put wherever you put the X line is, then you decide where the Y and the Z automatically go. So, but you can put it in any place, as long as when you're measuring two things, you have the same X dimension, then you can make comparisons. You have a common placement of the dimensions. Because they all equal kind of a circle in the end, but the point is that orientation is important for comparison. So that's all, it's an important aspect of this, which is a little difficult to draw because you can only do the two dimensions at a time kind of thing, which is a little bit irritating. So anyway, you're back to the E equals mc squared. So basically what you got is a mass is basically energy moving the speed of light. So you really don't need to quantize the amount of mass or energy, but the idea that Einstein used this speed of light squared as the constant, as the bit, as the quanta, is curious, because I think it was arbitrary, but it does come in handy in the sense that it's best understood that you're basically a bunch of photons. If I annihilate your material structure and just kept the mass of you, the energy, and then release it. Like a nuclear bomb, you're made out of photons. You're just made out of quanta moving the speed of light. You're convertible into light, I suppose, is the argument I'm making. His mass is convertible into light, or some form of photon, including those without frequency, which would be gravity, essentially, which is the field energy. But I don't want to get into the field energy thing again. Because for velocity, it's really not necessary. So what do I want to do here? So you know, it's that school of fish analogy. Is that the school of fish with all the fish in circles? They have, you know, let's say you have a school of fish and it's in one place. It's not moving. Obviously, every fish is somehow swimming in a circle. It might be a long circle. It might be all kinds of different kinds of circles, but it's a ellipse of some kind. It's some sort of roundy thing where they end up going as much in this way, as that way, and that way. That the opposite directions are equal, because it doesn't have a net movement anywhere, in the sense that it doesn't escape the boundaries of the school. So it's obviously circle in net to those boundaries. And that's basically what matter is. It's just a bunch of little bits inside moving in these orbits, these circular patterns. And they can be big circles, little circles. It really doesn't, it's really not the point, but they're moving essentially in those circles, and they can be doing it in spirals and, you know, all kinds of convoluted ways that would reduce their overall speed in terms of perceptual speed. Their actual, you know, like I say, if I spin something like a spring, you know, and I just rotate it as it goes forward, you can understand that its net forward progress would appear less than the speed of light, even though it's moving the speed of light through the spin, through the spring. Alright, so anyway, but that's not necessary to get into either. There's so many ways you can look at this, and when you get to the field dynamics, you almost don't need to have the motion dynamics, as funny as that sounds. I mean, you don't need, because it just becomes positions and probabilities of what direction a position is going to be in. And so it's almost like you just quantize all the fish in the school, give them a position, and then just say that position will, the likelihood it's going to have a fish going this way, or it's going to have a fish going this way, or a fish going this way, a percentage of the time. And that the entire field, as you understand it, because the field isn't moving, right? The fish are stuck. You could surmise that every position of fish, any position I get, I just say there's 1,000 fish in the school, I can have 1,000 positions, and I would know that every one of those positions would have to, in the end, have just as much this as it had this, as this, as this. So it could, you know, it has to, if it's spending 40% of the time going this way, it has to spend 40% of the time going this way, and then it only has the 10s left over, so it's going maybe 10 up and 10 down. But it always has to have that balance, because in the end, it's balanced. That position doesn't go anywhere. It doesn't fly out of the school, effectively. And so as a mathematical abstraction, modeling the reality, you can just kind of take the individual movement thing out of it and just recognize there's a probability of fish being in a position, moving in a direction, and that will have equal time among the opposite dimensional places it could be moving. Alright, probably more convoluted than I needed. So I'm giving you more explanation that's probably necessary. So anyway, so the idea is you have the standing school, and it has all these fish in it. They're moving the speed of light, and they don't go slower, they don't go faster. And that what velocity is that something, or let's go with acceleration first. Acceleration is something coming in that school that essentially tells the fish, go this way. And in some proportion. And obviously for most speeds, like say if you did have 1,000 fish and they were all going at the speed of light, well, you could understand that to be going 1/1000th of the speed of light would be some kind of big number, like 10,000 miles a second or something, the 16,000 miles a second, something like that. And that would be a proportion of the overall speed of light would be each fish's percentage of the, well, I explain it better in here, the math part. But anyway, you know, that all you need is a tiny percent of the fish to be moving in a direction for you to gain speeds that seem to us to be very fast, but obviously relative to the speed of light, they're preposterously slow. So it's only a tiny percentage of the time the fish has to be moving extra distance in the direction that the school is moving. So if the school is moving 20,000 miles an hour, in fact, each fish only has to spend extra time going in this new direction, you know, 1/300,000th of that time per second. 1/300,000th of a second. So in every second it only has to spend 1/300,000th of the second moving in that direction, each fish, for you to have that 20,000 miles an hour movement of the school. So basically the fish can still do basically what we're doing before. They only have to gain a tiny bit of directional change to acquire a pretty substantial, from our perspective, speed. Okay, I think that's understandable. So the point is, what's the mechanism? How is it conveyed to these fish that you're going to change your direction? Or more specifically, can you understand that there's a big difference between me adding fish going in a direction, like I introduce new fish into the school that are going in a direction, and that those new fish, you know, if they're going the speed of light, would blend their speed into the speed of the rest of the fish, in the sense that they would bang into all the other fish and basically nudge them in the direction. And that you could take that, if it was say 10% of the fish, I added 10% more fish, that bleeding would lead to, you know, some kind of speed like 20,000 miles an hour, just by adding 10% of fish going in that direction. So that's a direct introduction of mass, or energy, as we would think of it as, and that would be bleeding the force through into the new thing, give it velocity, because it gained mass. So it's kind of like, an analogy would be, you're stationary in space, an asteroid comes flying by, and you see a handlebar on it, and you grab the handlebar. And so now its velocity, its fish, are basically pushing your fish. I mean, I know it doesn't sound like they're pushing, but they're really pushing. Even though it looks like they're pulling, they're really pushing. But that's a whole nother explanation. Alright. So, the point is, I'm going to get to that explanation in this, somewhere in this video, just because I'm trying to explain why I don't want to do it in this paper, though. But just because it, just get a little more complicated. But anyway, we're still stuck with this. How do I tell the fish to go that way? Now you can sort of understand that it doesn't take energy. Like, when fish change direction, they have a thought in their head and they change direction. It doesn't take any real energy for them to change direction. You can sort of think of it that way. And if I turn all the fish into little BBs, little mindless BBs with a direction, you can sort of understand that, okay, they're trapped in orbits around each other, so that's the force holding them together, and that for some moment of time they have to stretch that force. They have to go more in one direction on that orbit. They have to move a little bit more this way, and then they're going to go back the other way, and that each little fish has to do that, but the whole thing will stay together because the force holding them together, the gravity, still exists and still there, and they're just going to start being a rolling orbit. The orbit's going to roll. So this is the part where, I also don't want to go into this in this document, is that's where you get the whole idea of time dilation, because obviously when I start rolling the orbit is slowed down, and that's time dilation. Alright, so anyway, so we're still back in how to convey this through the fish without adding mass. And, you know, that's where you have to get the field involved. You know, the field can kinetically hit it. You know, if they're all little BBs, you can imagine, well, I can just hit it with a BB and the BB will knock it in the direction I want it to go. And so, and then leave in some other direction. So I can basically give it the direction. I can bounce a BB off the back side of it, and it'll push it in the direction essentially I want it to go in. And there's real no energy loss, right? The BB I shot at it bounces off and goes exactly the same speed and has lost no energy. So the one that's bouncing off hasn't lost any energy, it's just changed its direction. And the one now inside the thing moving in the direction I'm trying to acquire velocity in, likewise, it was going, say, this way or that way or some other way, and now it's been hit and it's now going this way. So it's now going in a direction. So the two things exchange direction, but both of them have exactly the same amount of energy. They're quanta, they're little indestructible BBs. They did a kinetic reaction and they exchanged direction. So if I hit the school of fish, the school of BBs, with a bunch of little BBs, those BBs will bounce off, and they'll give the thing their direction. So they'll acquire the direction of the thing they hit, and they'll give the thing the direction they had. So that's basically the essence of the exchange of directional information through what we call sometimes a transfer of energy, but it's really not a transfer of energy. It's not a conversion of energy. It's just a change of the directional identity of the fish. I've basically told the fish, now you have a new direction. I've changed the percentage of fish moving in that direction. And that's all I've done. I haven't done anything, I haven't changed any dynamic of material things existing and moving. There's still the same number of material things in the universe, and they're still moving the same speed, all of them. And the only thing that's changed is some directional information was exchanged. So that's the point here, is that acceleration is acquired through this mechanism. And nothing more. It's that simple. You carry the force of your velocity in the sense that you have extra fish. I mean, some of your fish are spending extra time going in a direction. And if you hit something, then you'll lose that because you're now going to have your BBs hit something else and bounce back. And so now you're going to have exactly the opposite reaction thing's going to happen. So when you hit something else, you'll lose your velocity and essentially give it to the thing you hit. So the big pieces of matter end up behaving a lot like the little pieces of matter, except we know in our real world we crush, we slow down, we do lots of things that aren't kinetic, that aren't 100% efficient in their kinetic reaction. We make noises when we crash, and we do lots of things where we lose energy, where stuff goes somewhere else, and it goes somewhere else at some eccentric speed, even though little bits inside are still going the same speed. It's purely efficient on the quantum scale. It just appears on our scale to have some sort of inefficiency because we see things like heat as waste. But heat is quanta, it is these little bits, so it's all conservative. And we know it's conservative. People, physicists, they understand that yes, there's a conservation, but it still looks like there's an inefficiency to the reaction that isn't as obvious as a pure kinetic reaction. Okay, that's probably a good enough way to say it. So anyway, so that's the nature of acceleration and how it's exchanged. And so it's exchanged pretty much like the little BB thing, except obviously it has inefficiencies where our force isn't conveyed as completely and as accurately as the force on the kinetic scale. The BBs do it better than we do it in the sense that it's more complete a reaction. It's one action, complete action. where our conveyance of force takes time. A BB happens instantaneously, direction is exchanged. For us, it can take a great deal of time for all our BBs to hit their BBs and to do this exchanging of force. Alright, so that's really it, right? So that's the initiation, how you gain your velocity. So in the example of gravity, obviously we have to go that step further, and I have to remind you that there's a kinetic field of BBs in space surrounding us, coming at us from all directions. It creates a pressure, and that pressure is what is conveying the kinetic information through us, which orients us to attempt to create an imbalance in our BBs, more BBs moving down than moving up, and that's our acquisition of velocity, but that we're stopped because the Earth is here, so our velocity is retarded. So all we have is the acceleration component. We keep getting accelerated down, but we can't maintain the velocity because we keep losing our BBs to the surface we're standing on. I'll be back. Alright, let's see, where was I? Something like gravity and yeah, my arrows, my BBs, and they're hitting whatever I'm standing or sitting on, and that is absorbing their directional information, so to speak. And then gravity shoves another pile of it through me, and the ground absorbs it again, and it's just that kind of process. So I never gain any velocity, even though at any one moment of time, I probably have an imbalance of 10 meters per second going down. I mean, whatever that equals, 1 in 300,000 of my BBs per second is going down out of its normal orbit, eccenterized its orbit, spun, rotated, moved more in this direction. That means it spun further up here than it spun down here in the opposite direction. So it went more this way than it went that way, and so all my bits essentially just rolled down, and they hit the ground, and the ground pushed them back when it exchanged the directional information. My direction went into the ground's direction went into me. Yeah, that's simple. So yeah, that's and so then normal other accelerations would be you push something, you know, in some way contact it, and in that contact you're basically doing the same thing. Your bits are going to transfer directional information, and you're going to have the equal opposite reaction, and it's going to have your velocity that you, by how much BB you gave it, how many BBs force did you shoot through it in the direction, and that they got exchanged, they took that direction, how much of that thing's force, which was no force or whatever, the other direction, you're going to sense the pressure of that encounter. And you know, the interesting part of this, when you get into this whole velocity thing, is that it's kind of curious that we have this intuitive way of thinking about the world, in the sense that if I take a bullet going really fast and I shoot it into something and the bullet starts to deteriorate, you know, or even gets hot in the atmosphere or something, what's really happening is the velocity is destabilizing your orbit. So the faster you're going, the more destabilized your orbits are, and now little tiny things can break you apart because you're unstable. The strength of your atomic structure has weakened. So it's not like the bullet falls apart because, or gets deformed because of the real force impact. It's really deformed because it's weak. It's weakened by its velocity. And so even a tiny little piece of dust, you know, can just blow up a whole spaceship if you have enough speed when you hit it, because you're so unstable that even a little piece of dust just minding its own business will rip you to pieces, go right through you, because your force field has broken down. The thing tying your matter together, strengthening it, is weakening because you're moving, and it's breaking down all that, those orbits that are so binding. Yeah, so I mean, it's just a way of understanding the whole dynamic of things melting and things doing different things. You can understand it as an inertia issue, as a there's too much force going through something, too much energy, too much directional transfer, and it's breaking down these orbits, and it's the orbits breaking down that's releasing the energy and the photons and all of that stuff. So it really does go all the way down, sort of to the quantum bits. Alright, so the other thing I wanted to get to is that, let's see, I've covered, barely mentioned the field, but you really don't need that for this velocity thing, and barely mentioned time dilation, which is, you know, a subject you don't want to get into in this subject, because you're basically saying you've got it wrong. Time doesn't dilate, metabolism slows down. So obviously in the thought experiments that are described regarding relativity and space-time, there's nothing really taking place but a kind of cryogenics. That the faster you go, the slower your atomic metabolism, and it just slows everything else down. I don't think it'll do it in any kind of coherent way. So at certain speeds, like the bullet, you'll start to just fall apart. You won't even need to hit a piece of dust. All you'll need to do is hit an electron, a proton, just the tiniest of elemental structure material structure will be able to annihilate you. As a form, as a structure. You'll just break all the orbits. The galaxies will fly apart, so to speak. Okay, so what was the other issue? Yeah, so I just want to get to this, the idea. So when something has velocity, the idea is that there's this excess arrow. Okay, so just imagine there's a whole bunch of arrows and that you have a net excess of this much arrow. You know, there's this much more arrows going this way than are going that way. Now the trick is why wouldn't they just fly out of this end, you know, and just, that'd be it. Oh, they got away. They went outside of me, and now they're gone. And but somehow we retain our velocity. It's self-generating, and it's self-regenerating. So somehow this imbalance doesn't escape. It doesn't go away. And that's really in the nature of this idea of the, you know, I've sort of pointed out, I think it's a square orbit. You know, it's all kind of, everything's just kind of a square orbit. But anyway, it doesn't really matter. So we'll do circles now, just for the sake of making this point. So what's really happening is little bits are in little swirls, little galaxies, so to speak. Galaxies are kind of swirly, so it kind of gives you that idea of a spiral. It's just, you know, a wheel spinning. And so you can just kind of think of everything as being this swirl thing. And it has a probabilistic pressure that holds it together. So it can go a certain amount out and a certain amount in and a certain amount out. And it kind of works out that in the end, it's going to stay together. It's got enough elements that no matter a little jolt, it can take it and it'll re-find its balance. It'll cleanse itself of any impurities, so to speak. But the trick is that there's this area out here, you know, outside the gravity, so to speak, the strength of the gravity, that is kind of fuzzy, you know, that has this motion, but it has it like by 50%. I mean, it's much dirtier. It has a lot of other movements in it. So you're basically everything, all the quantum that is trapped in orbits, it's all, every one of these things, a quark, an electron, a proton, a neutron, they all have a fuzz around them, a field of a kind of sympathetic swirl, where there's this probability of finding bits that are still going this way and this way in this circular way. So it like extends beyond us, and that's what the shadow thing is in the two slit thing, where I was talking about the fact that we cast fuzzy shadows. Is that's really another example of the fact that around me is a swirl that is a kind of a weak kind of matter. My matter doesn't have a this is where it begins and this is where it ends. It has the little swirly atom might end here. This is probably not a great, this drawing kind of sucks. Okay, so this is the atom. This is where the atom ends technically, but practically the atom still has, well, I've been spinning the wrong way. The atom still has this sympathetic swirl fog, so we call it swirl fog, around it that's sort of sympathetic to the spin of the atom, generally speaking. So there's a sympathetic motion. So like around the galaxy, if we use galaxies as an example, there might tend to be a loose structure of little bits around it, very small little bits, and that those little bits are almost creating a flow of their own, an eddy, a mechanism. That's certainly not as strong as the suns that are bound by gravity. It's still kind of bound by gravity, but it's much weaker, and the matter is much more dislocated. So the bits are more dislocated. So these would be just quanta. No quarks in here, no protons, no neutrons, no electrons in this field, but just a loose field of quarks that just of quanta that just tend to be going in these directions 50% of the time, let's just say. They're doing this rotation 50% of the time. The other 50% they're doing is going all over the place. But the tendency is they're doing this. So what's basically happening when something's moving is that anything that's, all the arrows here that are trying to escape, right? So this little atom is moving in this direction. Well, what's happening is when the arrows come out this end, they're kind of being swept, as funny as that sounds, by this current. And what the current does is it starts grabbing them here, so to speak. The current just keeps pushing with the flow. And so they tend to start close, and then they're doing the same thing, though. They're getting more and more distant because it's weak. So they're just going wider and wider and wider and wider. And by the time they get free, by the time they're so far out of this fog that now the fog has no control, now the arrow can go back into the atom. So that's basically what's happening, is it's going around and coming back in again, and going around and coming back in again, because it's following the sympathetic flow of all these spirals. So essentially all these atoms are probably lined up. I pointed out in another video that they're probably in some sort of pattern where all the spins are in the same direction. So you could have these as like galaxies, flat galaxies. I've drawn them not flat like a flower here, but you get the idea. They're flat, and they're all spinning in the same direction. They're all converging here, and so they'd all be coming out, somewhere at this other end. So if I drew this three-dimensionally, the spin is going in here, and it's coming out here. So this is again, this three-dimensional drawing would be something like that. But here would be the center, and it just comes out the center, goes around the outside. Now what does that remind you of? Oh yes, the magnet. So it's like everything already has those field lines, and what's unique about magnets is that those lines are polarized in the sense that they're only functioning in one dimension. But that's a whole nother explanation. But you can sort of get the idea that that's basically what field lines are representing. It's very much the same idea, and that it's a conservation of form. Essentially, how to say it in a more rational way. But it's that this thing is big enough that it can still hold its directional identity, because it is in a field, a thing that is itself a local field, and that local field has enough stuff in it that nothing can really break it. It just keeps being pulled back into to the field, and the field just keeps holding itself together because it doesn't let anything get past this edge of the fog. Nothing escapes the fog of its rotation. So it's kind of like the balance of a solar system. It can go on for a long, long time without breaking down. And clearly, like atoms that are radioactive, it is breaking down. There's stuff escaping the fog. You know, the swirly bits aren't being able to retain that conservation of the individual atoms moving. The quanta are moving, ultimately inside of everything, spinning. But the quarks and the protons and the neutrons are also moving, and they're doing it by having imbalances, by having more quanta going one way than they have quanta going the other way. So they're all little individual fields, and all the fields just keep adding up to a bigger and bigger field. And they're all conservative in the sense that none of them are letting stuff fly out. Like a galaxy and all this other stuff that they all seem to be held together. They're in some sort of balance with the energy around them. Now obviously I could shove a bunch of quanta at them, and I'll disrupt that balance, and I will allow stuff to escape, and they will lose mass, and shit will hit fans and such. So anyway, but that's the thing I wanted to get to, is this idea that what perpetuates the motion, and what's, something's forward direction, and what's perpetuating it is that there's a circle of fog that's essentially just always taking the directionality, and through some equation of math, like I said, it just gets wide enough where it's now so far out that now it's liberated, and it's liberated when it's behind the thing it came out of. And that's the dynamic but that's the skin of everything. Everything's skin. Every field barrier has that fog in it. And the fog can essentially be, you can think of that as like when two things are combining with each other, or connected to each other in some way. The spin dynamic is such that this ends up being fog. The fog here and the fog from this thing, those fogs combine. And if they're conducive, constructive, or destructively interfering, essentially the fogs. So if they're spinning in opposite ways, the fog will be destructively interfered with, and now you're more likely to create stuff that will escape. And if they're constructively going in the same direction, their capacity to hold together their identity, to retain their identity, becomes even stronger, because they share now twice as much energy, so to speak, twice as much fog energy in the same direction. So they're even more likely not to lose an arrow going this way, because it's even more likely they'll get sucked up in that vortex between them. So if they're both spinning, let's say this way, and they have a motion this way, that motion will come out, get caught in the vortex, and be spilled right back here again to be reabsorbed as new acceleration, essentially. So whatever velocity you lose through the force leaving you, it never really leaves you, because you're going to regain it as new acceleration. So anyway, so the point I want to get to is just that this is all of this, these spinning fields, is the whole nature of the thing, and the fact that you can have this constructive and destructive interaction between fields or fog. I have to come up with a way to describe this ambiguous zone where you go from, this is gravity strong enough to hold something in, this is freedom. Okay, not enough gravity to hold a quanta. And this space is a certain distance. So there's a certain distance, okay, between the point where you're locked in the orbit and the point where you're actually free. And it's not like we sense it from planets, that it's some sort of absolute thing, that it's a space that might be very small, like a little increase in your velocity and I shot you out of your orbit, that kind of thing. A little change in your if I push the planet a little bit further away from the sun, that it'll fly off eventually. But it's not a really tiny amount of space. It's kind of a large amount of space that you have to play with. And especially in these atoms, the space around them, the 50% space, the space that is this weak gravity, might be many times more, might be a much larger diameter than the actual diameter of the atom. So the field strength of this atom might extend fairly far, fairly distant, in terms of that probabilistic spin that is really just residue that spun off of this thing at some time. So these are really just failed orbits. You could almost see it like an asteroid belt even. I don't know, it's probably not a very good analogy, but just think of it in that sense, that it's just this field of lighter pressure, lighter gravity, but still enough to create a stream that will bring things home, boomerang them back. Probably not great metaphor. So that's probably the reason why I made this video, was just to come up with some sort of, maybe I'll come up with some terminology to attempt to explain some portion of this in this video on inertia. I mean, this paper on inertia. But like I said, I think to defend this new theory of inertia, I don't think I have to necessarily go this deep into explaining causes, as so much as just state that there's a mechanism that exchanges direction, that interior to atoms, they hit each other, they exchange directional information, and that's enough to explain essentially velocity, as long as you understand that that directional information can't be lost until they make actual contact with another field of force. They have to penetrate some other piece of matter's material form and exchange kinetic information to lose their velocity. Yeah, I think that's probably, I don't want to get too far of the field. So yeah, I don't know how far to go. I don't know how far it will be necessary to get this published as an explanation of inertia, which I want to limit the paper to that subject. I really don't want to have to do gravity and magnetism. I mean, I said clearly that I have no obligation to do magnetism from here, beyond the fact that magnetism has to do with all the same exact mechanisms, except with the idea of polarized in single dimensions. So anyway, yeah. So I'll get to that. But that's basically the idea. The idea is that you have a core, just like your center of gravity, and your core is where most of that movement's taking place. Most of those extra arrows that are going in the direction that you're moving, accelerating, well, most of them are moving through that core, and they're coming back out here around you, and yeah, that's the current that maintains your velocity when you have a velocity. Like I said, we don't really technically have a velocity because we're just stuck constantly accelerating, and we're constantly giving away our force into the ground and taking the direction of the ground, which is clearly opposite to the direction we're moving. The ground has clearly got some opposite arrows because clearly we're hitting it. Okay, so that's probably enough. Yeah, I think that's good. So not bad. Well, anyway, so the other thing I'll do is maybe I'll leave a link on the paper. And so if anybody wants to comment on the paper, they can comment on this video. So I'll leave a link on the paper to this video as the place to comment. And I'll just establish that this is the video on inertia. And, you know, if I have to do a future video, which I probably will if I finish writing the paper, so what? Yeah, maybe I'll disable comments and direct comments to this video. So all the comments on the subject of inertia will now be on this video. Yeah, that's a good idea. Okay. So, till next time, and such.